Today we're going to talk about simple harmonic motion, and a simple situation is block on a spring. If I were to take this block, stretch it this way until this edge, which was at x sub m, which is its maximum amplitude, and then released, it would just oscillate between those 2 points without losing energy, because this would have to be a frictionless surface. And that frictionless surface is necessary for us to call this motion simple harmonic motion. If we were to make a graph of this motion, where the y-axis was the displacement and the x-axis was time, when I release the block at time equals 0, it would be at its maximum stretch. And then it would pass the 0 point and reach its maximum compression, and we would get a cosine function for that oscillation. Between the two crests would take a time that is equal to the period of that oscillation. Our equation for this type of motion is the position at any time t would be equal to the maximum amplitude times the cosine of omega t plus phi. Looks complicated. Omega is the angular frequency phi is the phase angle. We've already defined xm as the max amplitude. In order for this to be simple harmonic motion, these three have to be constant. If those aren't constant, then we can't call it simple harmonic motion. Let's look at what happens with these graphs if we change one of those values and compare it to the original. All right, so in this situation, if we say that the blue is the original situation, the red would be if we were able to change the angular frequency so that the period of the blue is from this crest to this crest, but from the red, we're cutting that period in half. And the period is related to the angular frequency. What stays the same is the other two variables, which is the maximum amplitude and the phase angle. I'm sure you're wondering what the phase angle is, so let's look at that next. So here's where the phase is changing, where most cosine graphs start off when it's 0 at the maximum. The phase angle would be starting our observation when the object is not at its maximum. So it would already be in motion. That's it. So here is where it reaches its maximum amplitude. So it would be like starting our stopwatch as it is moving towards that maximum displacement. So if we were to have two springs that were identical, two masses that were identical, and we stretched them out but released one before the other, we would have a phase angle. They would just be out of phase. If you release them at the same time, this red graph would be right on top of the blue graph, and everything would be exactly the same between them since the mass and the spring are identical. So the other value to change would be the amplitude. So two springs identical, two blocks identical. We stretch them out to different positions, starting positions, and release them. The graphs will overlap, the periods will remain the same. They just won't reach those maximum displacements. So let's look at this graph with this equation again. Now that phase angle is going to be 0 unless they give you the function. It is almost never written in the problem. So that simplifies this down. All right, so now we're just left with omega t. So when the object is at its max amplitude, so at that location, we need to make sure that this function equals 1, so that the x at the period is going to equal xm, because that would take one period from 0 to here to return to its original starting point. Now, if we utilize that information, we see that when t is equal to the period, that omega t would have to equal 2 pi radians, because it has to go through an entire cycle. It's synonymous with an object going around a circle. If an object starts here, it'll have to go 2 pi radians to get back to where it started. So I'm going to substitute that there. So omega times the period would have to equal 2 pi. So that omega would equal 2 pi over the period. Or, since the period is 1 over f, 2 pi times the frequency. Now let's think about these, some other graphs that we can make with this. So we know that the position graph will be the cosine function. Now that would be is if we pulled this block again and it's sitting here and we released it from this point, it will accelerate in this direction due to that spring force, so that the velocity will be negative. All right, but at the point when we release it, it's not moving. And then it's going to accelerate until it hits the 0 position. And then it's going to stop once it reaches the negative maximum amplitude. So that the graph of the velocity as a function of time is going to look like that. Now, if we think of a position as a function of time graph to a velocity as a function of time graph, we know that the slope of the position time equals the velocity time. So if we look at the slope at time equals 0, it's a 0 value, so we have 0 velocity. Then the slope starts to increase negatively, so the velocity starts to increase negatively until we get to the maximum slope, which would be the maximum velocity. Then the slope decreases until it reaches 0. So here the velocity is decreasing until it reaches 0. and then it reverses. Here the slope is positive, which means we have a positive velocity, all the way again until we hit a zero velocity, okay, all the way through. All right. Now, thinking of the block oscillating again, we have the acceleration of the block. We can just look at the velocity as a function of the time graph. Here we have the slope start out as negative. At that point, it's 0, becomes positive, so the acceleration rate goes from the biggest value to 0. So it's going to start the biggest negative value, go to 0, reach its biggest positive, go to 0. Okay. And if we look, the acceleration graph is just the opposite of the position time graph. Now, if we think about this in terms of our equations, the position, and I'm going to omit the phase angle. Most of the time you will. For the slope, we can see, well, we could see, if I can expand that back out, that this is a sine function, but it's an inverse sine function. And we can get that from the derivative. So since dx dt gives us the velocity, so our velocity at any function of time is the negative sine of omega t. The xm stays there, but the derivative of omega t gives you omega. And then we can take the derivative of the velocity with respect to time, and we'll get the acceleration. And the derivative of negative sine stays as negative cosine. And xm stays there. And we have to take the derivative of the inside, which we get omega squared. Those are the equations for the value at any time. If we want to figure out what the maxes are, we have to figure out when do these functions equal 1. And when they do equal 1, we can see that the x at whatever time gives it its maximum, it's going to be equal to just the maximum amplitude. The velocity is going to be equal to just that, because the sine function should be 1 to get the maximum velocity, and then the acceleration would just be omega squared x. If we compare the equations to the graphs, so here we have a cosine function, here we have a negative sine function, here we have a negative cosine function, and that matches up with the derivatives of those equations. With most problems, you're going to be working with these max equations. And just another way to see these, this is equal to V max, or the velocity amplitude, and this is equal to A max, or acceleration amplitude. And those can be substituted into these equations in place of the omega x.